In the 12 years after Thomson's cathode ray tube experiments, Millikan did some experiments using small oil drops, and with the apparatus that he had designed, he was able to determine the charge of the electron. Now, if you remember, the mass-to-charge ratio for the electron was already known thanks to Thomson's previous experiments. So if Millikan nails down the charge of the electron, we'll know both charge and mass. So let's see how that happened. First, he measured the mass of an oil drop by looking at how long it took it to fall inside of a special little chamber that he had designed. And we're going to see that there's a whole lot behind the scenes on that measurement. We're not going to care about most of it for our purposes. Now, then he used some X-rays to create a charge on that droplet. Now that it's got a charge on it, he turned on an electric field inside of this chamber until he was able to get that one drop to levitate and hold stationary against gravity. So if you know the mass of the oil drop, you know the gravitational force on it too. As a result, you know how much force you're pushing against with it, and from that you can determine the charge on that electron. Now, this is what that apparatus looked like in a schematic form. This is a different one than we have in a lot of the books out there. You'll find lots of schematics around for it, and actually this experiment was commonly done in physics classes for probably a lot of the 1900s, but it ends up being pretty time-consuming and fairly expensive to maintain this apparatus. So you'll find lots of different sketches out there if you don't care for this one, and they'll all give about the same details. So you can see that the way that it handled. The first thing he did was he sprayed some oil drops into this apparatus with basically like a little perfume sifter here. So the small drops begin falling, and one of the drops is going to fall through this hole right in the middle of this positively charged plate. Now, some of them are going to pick up a charge just by friction when they bang into this, but most of them aren't. And even if they did have a single charge, they're going to pick up some extra charges as the X-rays hit into them. The electrons are knocked loose from surrounding air molecules by the X-rays. The electrons are going to stick to those drops and increase the number of electrons on it. So now we have more and more charge on here. Finally, he gets a drop in vision, and he says, that's one that I want to pick. And so what he's going to do is he's going to charge this plate and this plate, or rather change the charge between the two. That's going to get his drop to sit here and levitate. And all the other drops that are around are going to settle out. They're either going to fall down or they're going to levitate up and crash into the upper part of the chamber. Now he's got one drop. Now, since he knows the voltage between those, he can say, right, I know how much weight it's going to have based on that levitation. And so, with a whole bunch of mathematics after the fact, he's able to determine the charge of one of the of all of the electrons on there. And he was going to have a lot of different drops with different charge numbers on them. Well, so he did lots and lots of these drops and looked to see what increment they all increased by, and from that was able to infer the size of the charge of one electron. Pretty nuanced value. And it's all from balancing the force from an electric field against the force of gravity. Now, that said, there's a whole lot more to that measurement and the mathematics of it. If you want, you can search around online and you'll definitely find out more information about that. But it was a pretty thorough experiment to take a measurement of. Now, this happened in 1909, so like we said, about 12 years after we had originally come up with our current model of the atom, which is that there are going to be electrons inside of it, but that's about all that we know so far. Now, he repeats this for many drops. I think it was a few thousand or something like that. Measured the radius from each of the drops, along with the density and a few other things. He was able to determine the mass of each drop. Based on that mass and the charge that he had to use, he was able to determine how much force there was pushing the drop up. So when he got it to levitate, he knows the amount of force that's in there. From that, he can determine the charge. And it always ends up being some whole number multiple of a minimum charge. Therefore, the charge has to be part of the electron itself. If I got 15 electrons on that drop, it's going to take 15 times higher charge to balance the force of gravity. If it's only 14, it's going to be an increment of 14 or 13 or 12, all the way down. From that, he's able to determine the charge of the electron to be, well, you see the value right there on the screen. He's able to use Rutherford's mass-to-charge ratio to get the mass of the electron, which is a really good measurement. He was actually within 1% of the true value, or at least of the modern value. That said, something that's kind of interesting to know is that for a while there, everyone who repeated the experiment biased the number upward just a little bit, until finally it got to the current accepted value, which is a little bit higher than his original charge measurement. What that was actually a form of confirmation bias. It turns out that each person who did the experiment, they would say, well, you know, but maybe that one drop wasn't right because I see my values off a little bit, so I'm going to reject this one drop and this other drop too. And wow, look, now my agreement is almost the same. And over time, everybody kept stacking that up, and finally it did refine in on the true value, but there was that confirmation bias. Whenever you got what you thought was the right answer, you said, great, I've got the right answer, and you stopped looking harder. It turns out he had an older value for the density of the oil, and so when he did his math, it all came out to be just a little bit too low, still within 1%. And let's face it, he's using a charge plate and a perfume puffer, more or less, to do this really sensitive measurement. We now have it better known. Now, to give you some idea of the scales that we're working with here, the distance from the Sun to Pluto is going to be 5 times 10 to the 15th millimeters. That's going to be a pretty large number, right? 15 zeros after the 5. Take a look at this order of magnitude. This is a minuscule amount of charge when we're talking about the measurement in the units of coulombs. It's an incredibly tiny measurement that he had to do. And it kind of blows the mind when you think of it like that. Now, this is what the view of the atom is, circa Thomson and Millikan. And we often refer to it as the plum pudding model, where you can see that there's this uniform chunk of positive charge, and inside of it there are these small little chunks of negative, kind of like plums inside of a pudding, or if you'd rather think of it like this, it's like rice pudding or something like that. Either way, you got a whole bunch of dessert, and inside of it there are tiny little chunks, and those chunks happen to be negative charges. Now, that answers all the questions that they had so far, but there's also some other observations we can do that show that this wasn't a complete picture.